this session. And I want to introduce Shaun Clowes. He's come all the way here from down under in Australia with SecureReality. Is it true that the toilets flush opposite way than they do up here? There's lots of mysteries about Australia we're trying to clear up today. So anyway, Shaun's got a lot of material to cover, so please welcome Shaun Clowes.
Thank you. Okay, so as the introduction just said, my name's Shaun Clowes and I'm from Sydney, Australia. I work with a small consulting company there called SecureReality. And the title of my speech today is Fixing and Making Holes in Binaries, the Easy, the Hard and the Time-Consuming. But before I get started on all of that, I really should work out what sort of audience I'm speaking to. So of those in the audience, who would be familiar with binary file formats, stuff like ELF, other executable formats, PE, okay? Who would be familiar with disassembly, assembly, reverse engineering? Okay, fair enough. So as was just said, I have a lot of content, so I'm going to have to move through it quite quickly, so I apologize if I speak a bit fast. So, I guess the first thing I ought to cover is exactly what I plan on talking about today, because I'm going to be bandying around a lot of terminology. Some of it may not be the same as what you guys would normally use it to mean. But in essence, what we're actually talking about is we're just talking about changing the behavior of programs. We're talking about modifying programs. But we're not talking about that in the standard way which it's done. In general, software is obviously modified by changing the source code, recompiling and rerunning the executable. We're not going to do that. We're going to modify the program directly in its compiled form. So we don't need the source code for the program and we don't need to recompile it. And in some cases, we don't even need to execute it again. So there are actually two basic types of binary modification which I'm going to be talking about today. One is static or executable file modification. So that's when you modify the executable in its on-disk file form. And there's also runtime or process modification, which is quite interesting, where you actually modify the program in its running memory image. So while the program is running, you modify it. So I guess it's a little bit of a glib question, but we do have to ask, why exactly would we want to modify binaries? Well, modifying binaries is exactly the same as any other way of modifying executables or modifying programs. You want to do it for the same reasons. You want to fix bugs, you want to add functionality at times, and sometimes you just want to change the way in which the program currently works. You want to make it behave differently for some reason. So then the question becomes, why not just use the source? Well, there are lots of reasons for this, and I'm sure all of you can think of a number, and the most obvious one is that you simply don't have access to it. And that's obviously usually the case with common off-the-shelf software. Every enterprise is using a hell of a lot of software to which it does not have the source and will never get and will never get access to. So we can use this sort of methodology and approach to modifying that sort of software. But there are other reasons which perhaps aren't thought of as often. One of them is when the source isn't readily available. So in that case, we may actually have access to the source. It may be something which we wrote, 4 years ago, and it's been in production ever since, and now we have this problem, so we need to fix it. But how can we do that when the source code is hidden on a disk behind everything else in a cupboard somewhere and no one has any idea where it is? So in that sort of situation, if we can modify binaries reasonably easily without an extraordinary amount of work effort, then it may actually just be easier to modify the compiled program than it would be to find the source. And finally, one case in which you simply don't have the option of using the source is when you're trying to modify a running program. Obviously, in a lot of cases, I'm sure a lot of you run networks and services which simply can't be down. You have 5 nines uptime on those services and you can't bring them down. So if you need to change them, what do? You can't just get a new copy of the program and stop the running service and then run a new one. In this case, you have no option to restart it. You don't have the option of restarting the service, so you don't have any other option but modifying the binary in its process form. And I guess one thing about this stuff is that it's always been seen as too hard. In the past, it just hasn't been seen as an option. People don't think about modifying binaries. They don't think in their everyday development life, if you're a developer, you don't think about, why don't we just modify the binary to fix this problem? And that's generally because it's always been seen as too hard. It's always been seen as esoteric, just something which no one wants to go near. But it's like everything, it really does depend on the value proposition. There are times when it is clearly a very good deal to modify a binary as opposed to any other form of trying to fix your problem. And that's because it's not always hard. It can actually be very easy, and we're going to cover a number of ways today. Some of them are quite easy, some of them are quite hard. And hopefully you will also agree with me that sometimes it can be quite easy to do this, and you might consider using it yourself. One thing I do need to point out is that while I say that some of these methods are easy, all of them do require some coding skill. You can't really do this unless you're at least reasonably proficient with C and have at least a basic understanding of what's going on. So I guess I ought to explain exactly how this is related to security, because I mean we are at a security conference. There are actually two aspects to this, and actually I'm going to speak about the second aspect first, because in the past binary modification has actually been used quite extensively, but it's been used by the bad guys. If you think about viruses, trojans, backdoors, all that sort of stuff, that's binary modification for you, and that's the bad side of binary modification. So that's the one which people tend to think of when they think of binary modification and security. But there is another aspect, and that's from the defender's point of view. The defender can use these techniques just as well as the attacker can to fix the holes which the attacker normally would use to get in, and they don't have to wait for vendor patches. I mean, the whole reason that full disclosure is around is because no one could handle the fact that vendors took so long to get around to patching problems. With this sort of approach, you don't need to worry about what the vendor's doing, you don't need to wait for the vendor, and you can fix the problem yourself. So binary modification is a very wide area. There's lots to talk about. There are a lot of platforms, architectures, binary file formats, and clearly we can't cover all of it today. So we're just going to cover a small subset of that, but hopefully a useful subset of that. So my speech today is actually going to focus on Unix systems, binary modification on Unix systems, and the techniques which we're going to talk about in particular are going to be very applicable to Linux and Solaris systems. And in particular we're going to be working on ELF binaries, so the binary file format ELF, we're going to be working on those sorts of binaries on Solaris and Linux, although most of the concepts which we're going to talk about are generally applicable elsewhere, and some of the concepts and even tools work on other platforms. But that's our focus for today. So, now that we've covered the basic introduction to exactly what it is that we're doing today, what are we going to do now? Where are we going to go from here? Well, initially we're going to have a quite in-depth discussion on ELF and exactly how ELF works, what ELF is, and what an ELF file consists of. And then we're going to straight into talking about file patching of ELF programs, and we're going to demonstrate how you can patch an ELF file to remove a vulnerability. Then we're going to talk about in-memory patching, which we can also use to patch running ELF programs. Then we're going to talk about library interception, which is a rather simple way of binary modification. And finally, we're going to be talking about Injector, which can be thought of as a runtime version of that library interception technique. So, obviously for what we're talking about today, since we're talking about binary modification, we're going to need an understanding of what a binary is and what the structure is of your typical, of an ELF executable here. The ELF stands for the Executable and Linking format. It was originally a Unix Systems Labs specification, but it's since been adopted by Intel's Tools Interface Standards Committee as portable binary file format for the Intel architecture. And since then, it's been used in virtually every recent Unix, AIX, HP, Solaris, Linux, BSD, they all use ELF, and that's because ELF is very powerful, as we're about to see. Very flexible. So there are three main types of ELF files. There are relocatable files, and they're object files which consist of data or code, and they are then linked with other relocatable files in order to become executables or shared objects. Executables being programs which can actually be executed, and run by themselves, shared objects being code and data which is meant to be dynamically used by executables at runtime. So it's actually only the last two which are particularly relevant to our discussion today, and we're going to focus on executables. This may be a bit obvious, but I just want to cover this quickly. There are two types of executables, static and dynamic executables. Static executables are entirely self-contained. Every bit of code and data which they require is inside the file and is there. So if you take the example of, say, printf, which is a very complex function and is used in most programs, what would actually happen is, in a static executable, all of the code of printf, everything required by printf is copied into the binary when it's compiled, and then you have a completely self-contained binary including all of the code to printf. Dynamic executables, on the other hand, use external data and code at runtime. They're meant to be dynamically linked with code and data which they need. And they do that by using shared libraries, which, as I mentioned previously, contain data and code and are meant to be used at runtime. And the benefit of this approach is that you end up with smaller executables because you compile your dynamic executable, you want printf, and all you have to say is that I need libc at runtime and I need printf from libc at runtime. And then when you're loaded into memory, the shared library is also loaded into memory, and you can work out where printf is and use it rather than having to have it inside your executable. And that also results in less disk and memory usage because the executables are smaller, so there's less disk usage, and there's less memory use because there's this one shared library which can be mapped into multiple processes at once. And that's why dynamic executables are much more common. In fact, on a typical Unix system, you'll be lucky to find many static executables at all. And all the vendors recommend that you don't ever use them. So almost all of our discussion is actually going to be related to dynamic executables. The ELF file format describes the two separate views of a file. There's a linking view and a loading view. The linking view is exclusively for use at static link time, so it's used when you're combining relocatable files or relocatable files with shared objects or relocatable files to create an executable. It's used by the linker to learn all of the information it needs to put all the files together to create an executable or a shared object. The loading view, on the other hand, is meant for use by the operating system, and it's used exclusively at runtime to load and execute the program to start it working, or in the case of a shared library, shared object, in order to map it into memory so that it can be used. So this is what a typical ELF file may actually look like. Every ELF file has an ELF header, and the ELF header provides a pointer to the section headers and the program headers. The section headers describe the linking view, and the program headers describe the loading view. And as you can see, in general, there will be many more section headers than there will be program headers, because the section headers are a meaningful view, and the program headers only have to describe enough so that the file can be loaded into memory. And each of the headers refers to offsets inside the file. Now, so taking a more in-depth look at the linking view, the linking view divides the executable into meaningful sections. Each section has a name and a type, and it can have a requested memory location if that section is meant to be loaded into memory when the program is run, and it has permissions if it's meant to be loaded into memory when the executable is run, and they can indicate whether the section should be writable or executable in memory. So some common examples there are down the left: interp, dynamic, dynsim, etc. But here are some important sections which will come in useful during our discussion. The .interp section contains a string representing the name of the requested dynamic linker for this executable, and we'll discuss the dynamic linker in much more detail shortly. The dynamic section contains all of the dynamic linking information for the executable, and that's used by the dynamic linker so that it can link the executable at runtime. The symbol table and the dynamic symbol table, they contain all of the symbols in the executable. The symbol table contains the local symbols used only inside the program, and the dynamic symbol table contains the imported or exported symbols. The string tab and the dynamic string tab are the partners to the sim tab and the dynamic symbol table, and basically they just hold strings which are used to describe the names of all of the symbols. The PLT contains the procedure linkage table, which we'll talk about shortly. relocation sections, .relocation .something describes the relocations over a particular section, and we'll discuss them more shortly. And finally, the simplest and the most obvious sections are the .text section, which contains all of the code for the executable, the actual machine code for the executable, and the data section, which contains pre-initialized data. Oh, okay. Yep. And then we have the data section, as I said, which contains the initialized data. If you look at the linking view, what you'll realize is that, as I said, some sections don't have a memory location, and what that means is that they're not meant to be loaded into memory at runtime. Those sections are simply for information. The information which is used by the linker to create the to create the executables or the shared libraries, or they just contain debugging information or other useful information from a system point of view. But that's actually the difference between the link time and the runtime. The loading view doesn't describe any superfluous information which isn't required to actually load and execute the program, and that actually makes it much, much simpler. And it divides the executable into segments, and each segment is either a load segment or an informative segment. A load segment describes a portion of the file which is to be mapped into memory when the executable is run. And the other types of segments, which are informative segments, describe the location of important data at runtime such that the system can find it. So each segment has a simple type. So if you look on the left there, you'll see some simple types: interp, load, and dynamic. They have a requested memory location at runtime, and they have permissions, read, write, or execute when they're mapped into memory, and they have a size, which can specify two different sizes. One is their size in the file, and one is the size in memory, where the system will pad it in memory, and we'll discuss that more shortly. So some of the more useful segment types for our discussion today are load segments, which, as I describe a portion of the file to be loaded into memory. The interp segment, which is actually a pointer to the dynamic linker string, specifying the requested dynamic linker for this executable. And as you would realize, that's actually the interp section. So there's this informative segment, which is actually a pointer to what would normally be called the interp section. And it's the same with the dynamic segment. It contains a pointer to the dynamic linking information or the dynamic section. So what that actually means is that if you look at trying to match up the two views of an executable, what you'll see is that you'll have some sections which happen to be meant to be mapped contiguously into memory, and they also need to have the same permissions. So in this case, you might see the interp, dynamic symbol table, and the text. None of that needs to be writable, so they may all be combined into one load segment with read and execute permissions. In addition, because the location of the interp string is needed at runtime, there may be an interp segment which is pointing where the interp string is. And it's the same with the data and dynamic, as you can see below there. They could be combined into, this time, a writable segment but not executable. And again, there's an informative segment to point to the dynamic table. And finally, as I mentioned before, you've got purely informative sections, stuff like the string tab and the symbol table, local symbol table, neither of which are needed at runtime, so they simply don't map to any segment. So portions of the executable will not map to a segment, but in general, all of the executable will be mapped to a section. So what that actually means is that all of the meaning, or all of the information which is provided inside the section table or the linking view is completely irrelevant in the loading view. It's absolutely not needed. And what that means is that the section information can be removed entirely from an executable, and that executable will continue to run. There'll be no problems loading and executing it. And this is actually a pretty good way to kill any tools which use the GNU lib BFD. Any of you guys who are familiar with tools like GDB and OBJDump, which do use that library, once the section information is removed, those tools will not work. They will rely on section information. One interesting thing which I want to point out following our discussion is that there are lots of really cool things which you could do with ELF files, lots of really amazing twists and turns which you could make, but while ELF is a really flexible file format, the operating system loaders, the routines which load these executables and start them running, aren't very flexible. And that means that they suffer from a lot of bugs and idiosyncrasies, and there are a lot of valid ELF files which won't load and execute. And there are a lot of completely invalid ELF files which will load and execute on these through these loaders, through these buggy operating system loaders. So the basic process of loading and executing an ELF executable is basically the first thing the operating system does is it opens the file, obviously. Then it loops through all of the segment headers and it looks for any load segments. Once it's found them, it memory maps them at the specified location inside the processor's memory image. And then it finds the interp segment, which contains the string specifying the dynamic linker. It loads the dynamic linker and passes it control, specifying some information about the executable, where it can find the segment table of the executable, where it can find the dynamic table of the executable. So we should talk about the dynamic linker and loader. It's going to come in quite useful later on when we start modifying executables. The dynamic linker is responsible for handling all of the runtime needs of the executable, all of the shared library needs of the executable. And to do that, it retrieves information, all of its information from the dynamic segment. And once it's found the information in the dynamic segment, it can then load all of the shared libraries which are needed by the executable into memory. And then it modifies the executable such that it can access all of the resources which it needs from those libraries. And we'll explain more about exactly how that happens quite shortly. So what's actually in the dynamic sectional segment? It's a pretty simple table which contains simple records with critical data about how the executable should be dynamically loaded. And it allows the dynamic linker to quickly find out all of the information it needs about the executable, meaning that the dynamic linker doesn't need the section table or indeed the segment table in most cases. Each record consists of a simple type, which is called a tag, and a value or a pointer. So some useful tags which we will be interested in today. A DT needed tag, which contains the offset inside the dynamics string table of the name of a required shared library. A DT rel entry contains the address of relocation entries, and we'll discuss relocation entries shortly. A DT jump rel, which contains the address of relocation entries, but only those which are relevant to the PLT. And the DT debug entry, which contains a pointer to debug information, which is provided by the dynamic linker, and that will come in quite useful, again, with some of the later tools which we'll be using. So looking at the final three steps of loading and executing an ELF executable, you map in the shared libraries by reading all the DT needed entries. So you find those shared objects and you map them in. Then you add those libraries to what's called a link map, and then you store a pointer to the link map inside the debug structure, which is referenced by the DT debug entry, and then you go on to perform relocations. The relocations tell the dynamic linker how to rewrite portions of the executable such that the executable can then refer to external resources. And each relocation specifies a dynamic symbol table entry to which it relates, and then the dynamic linker comes through and performs all of these relocations but based on whatever symbol is specified. And we need the relocations so that the program can use data which is in shared libraries, because obviously when the program was compiled, it cannot know where those things are going to be. When the program was compiled, it couldn't know where printf was going to be in memory when it was loaded and executed, where libc was going to be mapped. So that's where the procedure linkage table comes in handy. It's stored in the PLT section, and it allows the executables to call functions which aren't present at compile time. So for example, printf, like we were talking about. It's basically just a pretty simple set of function stubs. I'm not going to explain what the function stubs do before they've been relocated, but basically it's just a bit of code, and wherever the program wants to use printf, instead it makes a call to this function stub, and later on the dynamic linker actually rewrites these function stubs based on relocations such that they then point to the real location of printf. So you do a call to the stub, and then the stub does a jump to printf, to where the real printf is. And that actually looks exactly like that. Once the program calls the PLT stub, the printf stub has been modified by the dynamic linker, and it makes just a jump to the real printf in libc. The global offset table, I'm not going to talk about it much, but it's pretty much exactly the same thing except for data, stuff like standard error and ERR. And it's actually referenced by the PLT on the Intel architecture, which is why people often confuse the two. People often talk about attacking the GOT. In particular, you'll see a lot of people who've written format string exploits and are talking about attacking the GOT, when in reality they're really attacking the PLT. And I just want to talk quickly about the Gt Debug Record because it comes in so useful. Basically, it contains debugging information from the dynamic linker, which debuggers normally use to work out the contents of the program. In particular, for our use, it contains a pointer to a link map, which describes all of the memory layout of the process, including which files are loaded into the executable and where they're loaded. And that will come in useful when we talk about runtime process modification. So finally, we actually move on to some real stuff. We actually move on to modifying some executables. File patching. File patching is the most common form of executable modification that's been around for a very long time. Viruses use it all the time. Basically, it involves statically modifying the code as it's represented inside the executable file. And your basic needs are that you generally want to take the existing code, and then at some point you want to break the flow of execution. You want to jump out into your new code, which does something really interesting, different to what the program used to do before, and then you want to jump back to somewhere interesting again, once you've completed your new code. One of the problems with file patching, and the reason why generally it's not particularly common, is that you do need to understand the existing code quite well, and that can involve some disassembly and reverse engineering of the target executable. And in addition, your new code usually has to be written in assembly, although sometimes you can write it in C if you have enough space and are really suicidal. So the question then becomes, where are we going to put the additional code? One obvious thing is to just override existing code which you know isn't going to be used. But the question is, how do you know existing code which isn't ever used? It can be quite difficult to identify where you can successfully patch the program without killing it. So in general, that's something we don't want to do. We're after a generalized sort of way of doing this. One option is to use the section padding. There is a small amount of padding between the sections, but generally not enough. And worse, you have to find a section which happens to be in an executable segment. At least that's on any architecture except the Intel architecture, given that IA32, if memory is readable, then it's executable. We can also add a segment, which initially seems like an incredibly cool idea, because if we just add a segment, we can just specify we can add a portion to the file and then just have that portion of the file mapped in and have as much space as we want. But there are a lot of reasons why that isn't a particularly good approach. The code is very messy because there are a lot of ELF loader bugs and issues which to do with this. So if you do it, you'll find a lot of issues. So that's not the approach which we've taken today. Instead, what we're going to do is we're going to extend an existing segment. Basically, we're just going to add some more space into the file and extend that segment mapping such that we can have as much space as we like. And I'll explain that more shortly, but it's quite useful. And there are lots of other methods. If you're interested in finding some other methods, then I suggest you examine Unix viruses, Silvio Cesar's work. There's a lot of work out there on how to add some space to the executable. But the method which we're using is extending a segment. So if you look at basically what happens is that we have this portion of the file which is a few sections and they've been mapped to a segment. Then what we do is we just insert some blank space in the middle of the file at the end of that segment, pushing down all of the sections following the executable. Following that segment. Now, you can imagine that in a lot of cases that would cause lots of problems, particularly if the sections linked to each other using absolute offsets or something like that. But luckily, ELF doesn't work that way. In general, sections refer to each other using an offset relative to the section number. So if we insert space like this, there is no problem. Even though we've disturbed the layout of the file, we haven't disturbed it in such a way that it will prevent the program working or cause any difficulties. And so basically we can just extend this segment as far as we want and have as much virtually addressable space as we want. So let's actually take a look at a demo of that. So this is just going to be a simple demonstration, and for the demonstration I'm actually going to use a sample program. The reason I'm going to use a pretty trivial sample program is that although the methods are quite applicable to much larger software, we do have to have an understanding of the software, and it will be much easier from a reverse engineering and disassembly point of view to understand this simple executable than it would be if I brought in some big server software or something. So let's take a look at our sample program. It's just called login demo. And all it does is it brings up a username prompt, password prompt, doesn't actually do anything with it. But I mean, I guess if we were looking at this from a security perspective, one of the first things we might try, and it never works, but in this case it's going to, is we might do that and enter in a really long username and a really long password. Unsurprisingly, given that this is a demonstration, the program segmentation faults. So we immediately assume that there must be some sort of problem inside this executable with handling long usernames and passwords. So what we're going to do, in order to get a better understanding, we're going to use a tool called ltrace on the executable. For those of you who aren't familiar with it, ltrace traces all of the shared library calls which are made by the executable and prints them out on the screen as they're happening. And by using the -i option, I'm also asking it to show me the address from which the function was called. So if I run ltrace, I see a couple of libc setup functions, then I see an fputs in order to put the username prompt, fflush, and I see an fgets which is waiting for my input. So I enter in a really long username, and I see a call to strlen for some reason, not sure. Then I see what's almost certainly going to be the culprit in our particular investigation. I see a bare string copy with what looks like our long input, our long username, into a variable on the stack at bff418. And then I see another call to fputs for the password prompts. So if I enter in a long password, I see another call to strlen for some reason. Once more a bare string copy to a different buffer on the stack. And finally I see a segmentation fault, because obviously I've overwritten something important on the stack. And in this case I can, sorry? Yeah, but that wouldn't matter. Sorry, the question was login demo compiled with debugging, and yes it was, but it wouldn't matter. In terms of ltrace working, that wouldn't have any effect. ltrace works on programs whether or not they have debugging information in them. So finally I see a segmentation fault, and I can tell that I've overwritten save DIP because, well, we've got the telltale 41, 41, 41, 41 over in the instruction location portion of the output, which is obviously for capitalized. So let's take a closer look at exactly what's going on inside this executable, and then what we're going to do is we're going to fix it. Okie dokie. So if we look back here, we can see that the first string copy happened at 8048562. If we look at that in this particular, I can't see it. Oh, anyway, if you look at 8048562 there's actually an add instruction. So clearly the output from ltrace is actually wrong. It shows the return address rather than the address from which the function was called. So if we look at 8048555D, that's where the real call to string copy happens. If you look immediately above it, then that's where the destination operand is being pushed onto the stack. And the destination operand is EBP minus 10. So that's the base pointer on the stack minus 10 in hex. So that's 16 bytes. That buffer cannot, by definition, be larger than 16 bytes. So clearly that string copy should not be allowing any more than 16 bytes to be copied into that target buffer. If we look down further, for the second string copy, we can see it there at 80485C9. And again, we can see the target operand there. This time it's EBP minus 20 in hex, so it's EBP minus 32. And since we know that the other buffer was at EBP minus 10, we automatically know that once again, this buffer cannot be larger than 16 bytes. Now, so once again, this string copy should not be allowing more than 16 bytes to be copied into the destination buffer. So what we're actually going to do is we're actually going to make that happen. We're going to make sure that these are length limiting string copies to a maximum of 16 bytes. To do that, the first thing I have to do is add some space. To do that, I'm going to use a tool called add space, which is included on the conference CD. Basically, it does exactly what we talked about. It extends a segment and adds as much space as you require to the executable. So I'll just do that now. The source is included on the conference CD. Okay, so I asked AddSpace to create a new executable called fix login demo, which is a copy of login demo, but has an additional additional 1K of space added to it. To do that, it extended one of the segments and it created me new virtual storage at 8049754. If I take a look at that using readelf, and I take a look at the segments in the old executable. By the way, if you guys aren't familiar with readelf, it's another tool included with the bin utils. It can be used for examining ELF files, and it's much better than objdump. So if any of you guys were thinking about that, this is the tool to be used. So if I look at the old login demo, I can see the two load segments there. And we can see that one of them was size 642 in hex in memory. That's readable and executable, so that contains the code. And then we can see the second segment, which was of size F0 in the file and 110 in memory. And I'll explain more the difference shortly. But it's read-writable. Now if I look at the new one, this time I have two segments, but as you can see, the second segment has now been pushed. It's now 510 in hex length, and it's now read-writable and executable. It's been modified. So we now have a new executable. We've got some space. What are we going to put in there? Well, we're just going to put in some trivial code to fix the problem. For just okay, this is just some pretty bad assembly to patch this problem. Basically what it does is we have this call stub, as we were talking about before. The idea is to break the current chain of execution, go somewhere else, do something better, and then come back. So the call stub is meant to be put over the existing call to string copy, and what it does instead is it calls the code which is at 8049754, which, as you'll note, is the location of the space which we added to the executable. And what's meant to go there is this new code section below. And all the new code section does is change the existing call to string copy. Instead, it now calls something called ASTRL copy, which is just an assembly version of strl copy, which I hacked up. So you can see all it does is it pushes onto the stack the usual parameters, destination, source, and then the string length, which is specified as a maximum of 16 bytes. And then it calls off to 8049810, which is where it expects ASTRL copy to be. And then the problem should be fixed because it then just jumps back to the existing code. So what we need to do now is we need to apply that to the executable. To do that, we create what I call a code patch file. I just made up some simple tools to be used to do this, and they work on things which I called code patch files. Basically, a code patch file, all it does is it contains portions of data which are designed to be patched at specified virtual addresses in the target. So I need to construct a code patch file to do this. So I'll just do that now. So the first thing I need to do is I need to patch the first call to string copy, which is at 804.855D, and I need to put over that the patch stub. So sorry, the call stub. Okay, so I've copied that into our new patch file, which is called fix login path, sorry. Anyway, so that's the first string copy. The second string copy was at 804.855C9, and since we also need that to be an ASTRL copy of size 16, we can put the same call stub there. So 804.855C9. And then we also need to copy in the actual new code, which is expected to be at 804.9754. Okie dokie. And finally I need to copy in ASTRL copy, which is called by the new code at 8049810. Okay, so finally I now have a complete code patch file which should fix this problem. And as we can see, it just consists of 4 individual patches which are meant to go at those specified virtual locations. Now all I have to do is apply it. All that means is that I need to use a program which is also included in the conference CD called code patch apply, and all it does is it loops to all of the program headers, works out where the virtual addresses are, and patches those locations in the file. So code patch apply, and so I need to fix login demo. Okay. So as you can see, it goes off and it applies that patch at the specified virtual memory locations. Now if I run the new fixed program, it asks me for a username. If I enter in a long username, long password, nothing happens anymore. And if we do an ltrace of that, we'll see that it doesn't even call string copy anymore. As you can see, there's no longer any calls to string copy there. So basically we can use this sort of technique in order to fix holes in binaries. Okay, so what were the features, what were the good bits about that? Well, obviously file patching is very powerful. You can do anything you want to, you can change anything you want to about the target executable as long as you understand enough about it. And it's also permanent, so from now on that particular executable will never have that problem again. But the problem with it is that it's quite complex and it's very error prone. It's quite easy to end up with patches that just don't work or don't work in strange situations. The program must be restarted. Obviously you can't patch the file and then expect it to magically work inside the executable which is loaded into memory, and you can't easily, you can but not easily call new library functions. So if you want to call functions which aren't normally called by the target executable, then it can be difficult to get them, difficult to get at them. So now let's move on to a different form of patching. This one's in-core patching. This is runtime patching. It's basically exactly the same as file patching, but instead it's performed on the process memory image. All we have to do is we connect to the process exactly as though we were a debugger using the debugging supported on the platform. So that might be ptrace on Linux systems or procfs on Solaris systems. And we just apply code on top of the image. So where do we put the additional code? Exactly the same problem as before. We need to find some executable mapped space somewhere which we can use, except under Intel architecture since that's not important. But we can again try and override unused code, but we have to find it. We could also, in this case, use segment padding. Instead of section padding, we could use segment padding, and that's quite useful in this case, and that's going to be the technique we're going to use, because segments are padded to the end, to page boundaries. So their start is padded to a page boundary, and their end is padded to a page boundary. What I mean by that is if you take a look at this particular example of a segment, which is meant to be mapped at virtual address 8049644 for a file size of F0 and a memory size of 110, you'll see that when it is actually mapped into memory, it's actually mapped from 8049000 to 804A000. And what that means is that there's actually 1604 bytes of padding before the segment even begins. Then you have the segment proper, And then you have 32 bytes of nulls, which are provided by the operating system. Because the memory size is 110, the file size is F0, the difference being 32 bytes. So the operating system provides 32 bytes of nulls immediately following the segment. That's the BSS, for those of you who are familiar with it. And then we have, following the end of the segment, well, the real end of the segment, we can see that there's also some padding right up to the page boundary, so that's another 2,220 bytes. So basically there's a lot of free space in most executables which can be used for in-core patching. So let's actually do a quick demo of in-core patching. Okie dokie, so we're back to everyone's favourite program, login demo. But if we take a look at login demo one more time, okay, if you take a look at those segments, you can see that the first segment is mapped from 8048000 for 642 bytes in hex. That's actually mapped from 8048000 to 8049000. The second segment is mapped from 8049644. You may recognize the second segment since it was the one in the slides previously. And if we look at that segment is actually supposed to end at 8049754. But it doesn't, it ends at 804A000. So we can use plenty of space there in order to patch the executable. But something which is quite convenient is that if you recall our patch previously, it works based on virtual memory addresses. If you look at the addresses which it uses, 8049754 for example, and 8049810, these happen to be the portions of memory which are provided free to us by the operating system in terms of padding. So we can actually apply this fix on the running image of the process without any problems. It will work because that memory is just there. It's free to be used. One thing you might note though is that the second segment isn't mapped executable. That isn't a problem here because we're on the Intel architecture, but on other architectures we could as simply apply it against the first segment because it's got plenty of padding too. So basically all I have to do is if I just run login demo, and in another screen, all I have to do is I just run code patch core. All it does is it takes a patch file and it applies it against the memory image of a process. So code patch file, the target PID in this case is whatever the process ID of login demo is, and then the patch file, which was fix login path in this case. So I've got the running executable here, code patch core, it goes off and it applies the patch exactly as it did before, but this time against the memory image. And then if I enter in a really long username, a really long password, nothing happens. So exactly as before, we've just done exactly the same thing except we've done it while the process was running. So for example, you could use this to fix holes in services while they're running, 99% uptime services. So what are the features of in-core patching? Well, it's exactly like file patching. You can do almost anything you want to. In this case, it's non-permanent, which can at times be an advantage. Once the process finishes, obviously, the changes are gone. And it can be performed on any running process. But exactly as with file patching, it's complex and it's error-prone. It's easy to get wrong. And in this case, if you get it wrong, you generally kill the service at the same time. You have limited space for new code, well at least with the techniques we were covering today you do, and you can't easily call new library functions exactly as before. So now I want to move on to actually something simpler because those are the common ones which have been used quite frequently in the past for modifying binaries. It would be nice if we could cover something a little bit simpler which could be used by more people. Effectively by more people. So now we're going to talk about a different technique called library interception. And basically what this is based on is it's based on the fact that the dynamic loader is responsible for runtime resolution of all of the dynamic relocations. So we're talking about the GOT relocations for the data and the PLT relocations for the functions like printf. How exactly does it do that? Well, it reads the DT needed entries as we talked about in the dynamic segment. It loads all of the libraries which are needed and adds them to the link map, and then it goes on to process the relocations like we were talking about previously. So if you look at the process view, you've got the link map on the side which shows all of the libraries which are loaded into the process, and it contains pointers out into each of the pointers out to where each of the libraries has been loaded, the base address of each of the libraries. So when the dynamic linker is actually processing all the relocations, what it does is it looks through each of the libraries in the map in order. It searches all of the exported symbols, and it tries to find the matching symbol name for the symbol which it's looking for a function which isn't marked weak, which is just some detail in case you want to look into this further. But basically, the first match is the winner. So the first symbol name which matches the one it's looking for is the one which gets the relocation processed for it. So library function call interception is all about getting in first. If you get your library loaded first before the others, then you will be the winner for any functions which you export. And what that means is that you can then proceed to intercept any function call which is made by the executable simply by exporting that particular symbol. So, how do you get in first? Well, obviously one of the ways to do so is to modify the DT needed records inside the dynamic table. One way to do that is to overwrite the library entry for another library and simply make it point to yours instead. And then inside your library you open the other library to make sure that it can get whatever other dependencies it had on the old library which you just removed from the process. But that's a bit hairy and I'm not going to go into it, but it certainly does work. Another option is to move the dynamic segment and recreate it. So start with a whole new dynamic segment and then add a new library dependency before all of the others, higher up in the order than the others. And perhaps the much more common approach to this sort of stuff is to use the linker environment, and that's using the LD preload environment variable. Basically, the dynamic linker will use this environment variable, and any libraries which are specified in it will be mapped before any other libraries. The problem with that is that it doesn't work for set UID programs, and it doesn't work in lots of different circumstances. And it's been covered perfectly well before, so we're not going to go into it today. So fair enough, once you've managed to get your library loaded in first, what are you actually going to do? Well, you intercept the function, you intercept a particular function, and then in most cases you'll need to filter it in some way or do something groovy, and then you'll need to call the old function, or in fact the other way around. To do that, that's quite simple because the dynamic linker provides an interface which can be used by the program through the libdl.so library. It contains one function called dlopen, which can be used to load a library, and dlsim, which can be used to find the address of a particular function or a particular symbol. And if you specify the rtld next flag, basically exactly what happens is the dynamic linker ignores your library, looks through all of the others and finds the real one, the one which really should have had the relocation pointed to it. So let's actually look at something which we can do with library interception. In this case, we're not going to look at login demo anymore. We're actually going to look at a simple vulnerability in a bit of software, a well-known vulnerability, an old vulnerability. So basically, on this machine, I'm silly enough to run the Yahoo is daemon from Network Solutions. This is version 1.5.5. It suffered from a really simple to exploit remote vulnerability. If I pass an SOA query and I happen to specify %p, the reply, which is the error reply, happens to have a format string vulnerability. So you can see where it should have said invalid authority area, %p, instead it's given me pointers. So as you can see, this is a pretty trivially exploitable sort of vulnerability. There have been a number of exploits for this This is just one publicly, oh god. Oh, there you go, works second time around. Anyway, so this is just one of the public exploits for this problem. So as you can see, this is an issue which you'd want fixed. And if you imagine the sort of people who are running whoisd, they can't afford downtime in this particular service. This was being run by registrars, network registrars, people who had to have the service up at all times. So they would need to fix this problem as soon as possible. So what we'll do is we're going to try and use library interception to fix the issue. To do that, all I have is a really trivial library. It's called fixwhoisd. All it does is its initialization function just works out the address of fgets, and then it replaces the fgets. Basically what happens is that if you run an ltrace on whoisd, all it does is it calls fgets in order to read in the user input, then it goes off to process it and suffers from that format string vulnerability. All I've done here is I've taken control of fgets, I call the old fgets, and this time I check to see whether this is an SOA request. If it is, then I strip any percentage marks out of it, since I know that it suffers from a vulnerability. So I mean, that's what, 40 lines of trivial code. So all I really need to do now is to actually get that into the whoisd daemon such that it won't suffer anymore from the problem. So to do that, I'm going to use a tool called add library. And basically all I have to do is I run add library. Again, this is on the conference CD. So if I specify my input file, which in this case is the whoisd daemon, specify my output file, fixed whoisd, and then I specify the new library which I want to pick up. So that would be whoisd.so. So there we go. Now if I look at the library dependencies in the old whoisd, we can see that it needed the standard sort of resolution, DNS resolution libraries. Now if I take a look at the new one, as we can see, the first requirement, the first needed library in this executable is now our library. It's fixwhoisd. So that means that our fgets is going to be higher up in the order than anybody else's fgets. We're going to get control. So if I kill the existing whoisd and I start a new one, this time the fixed whoisd, you can see the message which has come from our library when it's been loaded. And now it should no longer suffer from this vulnerability. So as you can see, now if I put in the same SOA request, which previously used to be a format string vulnerability, my fgets is getting control and filtering it. So this problem doesn't exist in this daemon anymore. Okay, so what are the features of library interception? Well, contrary to previous binary modification techniques and the more common ones, library interception is easy and simple. It's quite trivial. Anyone with some C coding knowledge can make it work. All the interception code can be done in C. It's safe. It's pretty hard to break it unless, of course, your replacement function is really bad. And you can call any library functions anything you want to do. Effectively, you can write just standard C code and just have it picked up by the target executable. But the LD preload technique isn't permanent. The DT needed approach requires the library to stay there at all times. That library is now an important part of that executable. If you remove the library, the executable won't work anymore. And the program must be restarted in order to make this work, all this form of library interception. So on to Injector Ssh, which is a tool I wrote a while ago. And basically Injector Ssh is like inglib for Windows, in case any of you are familiar with inglib. All it really does is it injects a shared library into a running program. So you have a particular running process, you specify a shared library, and it forces that shared library to be loaded into the remote program. It's much harder on Unix than Windows, because under Windows the operating system provides quite a lot of support to allow this to happen. Under Unix that's not the case. There's very minimal support. So basically what does Injector Ssh do? It opens the process using whatever the debugging mechanism is on the platform. It searches the link map which is exported by the program in order to find the DL open function, which, as we specified, is a dynamic linker function which is used to load a library. It constructs the arguments to DL open on the stack. Note that it doesn't construct any code inside the target executable, it just constructs the arguments on the stack inside the executable. And then it forces the process to jump to DL open, setting the return address to 41414140, which is pretty much, well, in every case, an invalid address. So the DL open happens, the function ends with a seg fault, which is when it tries to return to the invalid address. That's intercepted by Injector Ssh. Then Injector Ssh can go on to call a particular function which is specified by the user, providing it the address of the dynamic segment if it wants it. And then once it's done all that, it restores the state of the process, restarting any syscalls which it was in the middle of at the time, and the process continues on running as normal. So the process is stopped for a second, loads the library, and then continues on exactly as it was before. That wouldn't be particularly useful if that was all that happened. Injector Ssh also comes with a utility object called intercept.o, which is meant to be linked into libraries which are going to be injected using Injector Ssh. And all it really does is it can be used to redirect dynamic function calls, exactly like when we were looking before, we got our library in first, so we got control of the functions. Intercept.o allows you to get control of the functions without having to be in first. So the user code provides a list of functions which it wants to override, and then intercept.o goes on to patch the PLT and forces the PLT to refer to the replacement versions, and then provides the injected library a pointer to the old function. So what it really looks like is this. If you've got a simple program, it's trying to call printf. When the injected library is loaded up, the intercept routines are used to break the link between the printf stub and the actual real printf in libc. Instead, it now points to the injected library, and the injected library can at its leisure call the old printf. So let's take a look at a demo of that. I think we've covered using this sort of technology for good pretty well. It can be used by the defenders to fix problems, but we should also cover how this sort of technology can be used by attackers. So in this case, instead of covering fixing a vulnerability, we're going to cover introducing a vulnerability into something. So basically, I've got again a pretty simple library. And it's called Backdoor Ssh. So I'm sure you can immediately have an idea of what it does. If you look at the code for this particular injection module, it has a few interceptions. It intercepts the PAM functions, which are used on most modern Unixes to authenticate users. It intercepts setUID, getUID, getEUID, which is obviously normally used to drop privileges. And it also intercepts read and write. So I'm sure you can take a guess the sort of thing which this library can do. And you'll also note that the entire library is 262 lines, and most of that is comment. So it's really quite trivial to do this stuff. So let's see actually what happens if we inject this library. So all I need to do is just specify Injector Ssh, and I will switch on all of the debugging, tell it that I want it to call the user function after it's injected the program, and by default it will call intercept begin to start interception. The process ID is the SSH daemon. And the library to be injected is backdoor ssh.so. Okay, so it goes off and it does its thing. I mean, if you guys are really interested in Injector.so and how it works internally, the source code's there, and the documentation from the last presentation I did on Injector.so goes into quite a lot of detail. But basically, it's gone off and it's modified the remote process and it's forced it to load this library. If I look at the loaded mapped files in the SSH daemon at this stage, as you can see, you wouldn't normally see this. If you look at the top, mapped from 4016000 to 4019000 is my library. So the running SSH daemon has now loaded my library and its functions have been intercepted. Let's see what actually this library can do. So if I log into localhost, actually, I'm not going to do it as me. So if I log in as a test user, okay, enter in my password, say I do an ls in my directory, you know, etc. Oh well, can't do that. Anyway, so I just log in as a normal user, everything's fine. slogin works the SSH daemon works exactly as it previously would. The problem is that it does stuff which it now shouldn't do. To demonstrate what I mean, if I cat the file temp evil, as we can see, what's actually happened is it's now logging from inside the SSH daemon, and we can see that it's intercepted the credentials, and it's gone username, test user, the response in this case was hello, that's not my normal password, and then we have an interesting message, automatic login not enabled, then credentials are set as normal. But in addition, if I do strings, so as we can see that login session happened in 3619, process 3619. So if I do a strings on temp evil 3619, there's all the session. All of the session has been logged. And in addition, it also has one other groovy feature. If I log in, this time I'm going to try and log in as a user which, you know, couldn't normally interactively log in. This, let's say, for example, bin, just any existing user. Localhost. Okay, it asked me for the password. How about the magic password? Let me in. And indeed, that's exactly what it does as root. So effectively, this running SSH daemon has been totally subverted in about well less than 200 lines of code. So, what are the features of this sort of approach? What are the features of Injector.so? Well, it's simple, it's flexible, it has all of the features of other library interception. It doesn't require any modifications to the binary, that is, once the process finishes, there is no remaining trace of anything which happened to it. There are no disk files, because you can delete the library once you've injected it. And the service doesn't need to be restarted in any way. So you can use this to fix vulnerabilities in running servers. The technical features of Injector.so, for those of you who are interested, there's unlimited space for code because of the way in which the library is loaded. There are no trampolines at all. There is no code injected into the remote target, which means that there's no executable or even writable memory required. You can call any library functions you want easily, and you can override any library functions you wish to easily. But it's not permanent, which can sometimes be seen as a disadvantage. So that brings me to the end of my speech. Thanks very much for listening. Are there any questions for anybody? No questions. This stuff has been well and truly done with Win32Ps. In terms of doing this on portable executables, Windows, not particularly. Sorry, no, I'm mostly a Unix guy. So, any other questions? Yep. Absolutely. Because of the way Injector connects to the remote process, the remote process doesn't even know that there's been a segmentation fault before Injector intercepts it and removes it. So when you think about it that way, previously the approach has always been to put a trampoline onto the stack, to write some code onto the stack and then cause that code to be executed. That way you didn't have to try and find somewhere else. But this sort of mechanism, because we're just doing it via this seg fault mechanism, we don't need to inject any code, and the process doesn't need to know anything or need to be modified in any significant way, other than would be normal with DL open or something. Any other questions? No? Okay, thank you very much.